Oh, thank you. Okay. So a divisibility rule is a shorthand way of determining whether a given integer is divisible by a fixed divisor without performing the division, usually by examining its digits. So we are trying to determine the divisibility rule of 13. Right. So when you divide the successive powers of 10 by 13, you get the following remainders of the integer divisions: 1, 10, 9, 12, 3, and 4. Why? Because 10 power 0 divided by 13, right?
Oh.
What would be the result?
The mod is going to be 1.
It's going to be 1. Why not? Oh yes, it's just 1. 1 divided by 13 is 0 remainder 1.
Yeah.
Okay. This here is 10 power 1, we get 10. 10 divided by 13 is 0 remainder 10. Right? 10 power 2, we get 100. 100 divided by 13. Let's do this. 100. We get 9. Okay. And then 10 power 3, this is 1,000 divided by 13, and then the remainder is 12. Here the remainder is 3, here the remainder is 4.
Yes.
Okay. So we can again that. Then the whole pattern repeats. So this pattern repeats. So it means 10 power 6, the remainder is 1. Is that so?
Let's try.
See that. 10 power 6. Oh, yes.
Oh.
The remainder is 1. And then 10 power 7, the remainder is 10. 10 power 8, the remainder is 9. So it's repeating. Okay. So therefore, we get the following method. You multiply the rightmost digit of the number with the leftmost number in the sequence shown above. And then you multiply the second rightmost digit with the second leftmost digit of the number in the sequence. The cycle goes on and you sum all these products. Repeat this process until the sequence of sums is stationary. So we have an example here. What is the remainder of 1, 2, 3, 4, 5, 6, 7 divided by 13? So what they're saying, you take the rightmost. This is the rightmost, right?
7. Yeah.
Yes. You multiply with the leftmost number in the sequence. The leftmost number in the sequence here is 1. Right? So it's kind of, you've reversed this number here.
You're given, then you multiply it in the number with the first number, like in order.
Yes, actually that's what I've done here. So they've reversed them. And then that is what you get with this sequence. 1, 10, 9, 12, 3, 4, 1. Okay. Therefore, the following method we get, so 7 times 1 plus 6 times 10 plus 5 by 9 plus 4 by 12 plus 3 by 3 plus 2 by 4 plus 1 by 1, we get 178. Once we get 178, we repeat that same process. Now, again, if we reverse them the other way, we get 871. It's this multiplied by 1 plus 7 you multiply by 10. 1 you multiply by 9, you get 87. And then you repeat the same thing with 87. Then you get 87 is stationary, right? From now on, the sequence is stationary. You always get 87. And the remainder of 1, 2, 3, 4, 5, 6, 7 by 13 is the same as the remainder of 87 by 13, which is 9. Okay, so we've reduced it to a very tiny one. And then with this tiny one, we can now get its remainder. Right? Okay. So the task that we've been given is call a t-shirt. Wait, what am I reading? Call cat. Goodness. Start from 13. Call cat, the function which processes this sequence of operations on an integer n, which is greater than 0. That will return the stationary number. For example, that 1, 2, 3, 4, 5, 6, 7, calculates 178, then 87, then 87, and returns 87. 3 to 1 returns 48, and 48 returns 48. Okay, so you can try this. I think that was.
Frank.
Yes.
What do they mean when they say stationary number?
So, for this given instance, after multiplying these things and adding, we got 178, right?
Yeah.
We repeated the same process on 178, we got 87.
Yes.
We repeat the same thing on 87, we get 87.
Oh, okay.
You try it on 87 again, you get 87. So now you're sure that you've got that number.
Okay.
Yes. So train. Right. So I think, okay, the first thing that we all agreed on is we need to reverse these digits, right?
Yes.
All right. So that is what comes into my mind first. So how can we reverse these digits? Let's go to, I have one here. You're trying to say something, John?
Yeah. I'm thinking first we can check what is the input type. It might be we are being given the number in a specific format. Do we have that information? Or might
Yeah,
we already know it's an integer.
Yes, we've said that n is an integer greater than 0. Yeah, it is.
Yeah, so thank you.
So I was going into the integer functions. I hope we have that. Oh, nice. So we have a function called integer.digits. It will give us a list.
Yeah.
So I think with this list, we can reverse it, right?
Yes.
Okay. So let's start there. Oh, no. So I would say integer digits. Okay. So now we have our digits. They have been reversed. So what should be the next thing that we're doing?
And I think
we need to multiply them, right?
Yes.
And then, so
We also need to have a list of the number 1, 10, 9, 12, 3, and 4, and 1.
We need,
But
so we need.
Yeah, what you say is correct. Yeah, but we can.
Yeah, actually, I was about to ask.
About it.
Yes, I wanted to ask, what do we need? Why do we need the list? So that you can do what with it?
So that we can do the mapping for when we are matching the leftmost of our digits of the sequence we've been given, and applying it to the rightmost of the digit times the leftmost of the sequence.
So does that mean, okay, let me just move to IEX real quick.
Yeah, but there is a interesting way of doing it where you rely on the same concept of modulo. Since we know we can't get more than 6 characters, like it starts repeating at the 6th digit. At the 6th, like if you look at the sequence, when only in the instances where it's between 0 and 5, that's when it only, like that's like the range between 0 and 5. That's when it gives you like a unique modulo for 13.
Just a minute. Let me just do this here. So this is our reversed list. It was 1 to 7. Right?
Yes.
And then, so okay, let me just put that list here as well. Have our, I don't know how to call it. This was 1, 10, 6, 12, 3, 4. No, actually up to this point, it's up to 4. It's up to 4, right?
Yes.
1, 10.
9, 12, 3.
3.
It's 3.
Yeah, there's 3 and then 4.
3, 4.
3, 4.
Yes, correct.
Right. So ideally, what these people are saying is, we take the first item here, we multiply the first item here, the second item here, we multiply the second item here. The third one here by the third one, the fourth one by the fourth one, the fifth one by the fifth one. If there's a sixth one, if there's one that is overlapping, what do we do now?
Start from the beginning again. You
start
from the sequence again.
Okay. So is there a formula that you can use? If at all, I'm just trying to think.
Yes.
If we have, there's how many? 1, 2, 3, 4, 5, 6, 7.
I think in this case, the multiplier is the solution.
Yeah. So do we think, okay, what I was trying to see, okay, like if at all we're using indexes, right? We can just use indexes to match them. So if at all we reach this here, this will be like the 6th, right?
Yes.
And then we come here, we don't find 6. What do we do? Do we take 6, we subtract the whole?
Yeah, you can subtract the whole length actually. That will also work. Or you can rely on modulo, because if you do subtractions, is at some point you will get like a number like 12, and then when you do like maybe the digit will have like 12 characters, and then when you minus 6, it becomes 6.
Yeah.
So using modulo like always reduces it to a number between 0 and 6, 0 and 5 actually. Okay, 0 and 5, yeah, because of array indexing. So if if you can maybe test it here on your you can actually test this on your
enum.count digits.
What are you going
7.
to? Yeah. Okay.
So you're saying we get integer mod. That is what I'm saying.
Yeah, sort of. Let
But-
me show you. So the idea here is no, but there's something here. There's something, Frank, we are missing. Okay, the idea is when we are looping through the digits, we can rely on the fact that as we're looping through the digits, we'll start with index 0. So we'll go 0, 1, 2, 3, 4, 5. Then at that point at which it is 1, it will be at index 6. Then at index 6, modulo 6 becomes 0. Of course, it's going to be 0 because it's the same number. And then the index of the multiplier will become that value. And then, of course, but you remember that as we are looping through indexes. Yes. So 8 to yes. Even if you go to like number 12, it will always come back to 0.
Okay. Yes. Yes. I think that will do it.
Yeah. So we figured out how to do the repeating bit.
Yeah, actually that can do it. So how do we know that? Can we just use reduce? Do you think we can use reduce?
Yes,
No, actually reduce.
do. It will do because we can get the previous accumulated value, and before we update it, we can check what's the current result.
Okay. Or we can also use
but
recursive functions, right?
Yes, I was coming to that. The challenge is the second bit where you have to check you have to run the same function, your result into your function again. Like you are updating your digits. That's where recursion is simpler.
Yeah, true. Okay. Let's move here. So we've said our mal. I'm going to copy this thing. Copy. Paste. Okay. So for round 1, we've simply said, I'm going to take for enum with index. Correct me if I'm wrong. Enum with index digits. Okay, and we've said what we'll do is take value. Oh no. Now this we need to have the accumulator somewhere. Right?
Yeah, so that's another thing. Could we this just getting the indexes. Could we play around with accumulator if we use enum with reduce? Like if we use reduce, and then part of the accumulator becomes a tuple of the index and the current value.
No, like the current sum.
Yes, current sum, yes. Then as we do modifications within the reduce, we also update the index, so we always know what's the current index.
Andron, are you with us?
Enum with index. what is the result type of with index? I haven't used with index myself, so let me get that.
So
Let me just
what this will
review
look
it
like,
here.
I can just do it here.
Oh, on
Don't know if-
IX. Simple.
I don't know if Brandon is still with us. This is what you get.
Yeah, this is actually this is perfect. Then this is like this works. Yeah, perfect.
Yes. So it is the value index.
And then just
I think I interchanged them.
yeah.
Okay. So we'll start with 0, right? Because we want the sum. And then we know at the end of the day, we'll get the value index is the accumulator. And then, oh no, this is the minimus function thing in there. That you can do everything you need here. Right. So you said we'll take this value. Times
Multiply.
it is the modulo of the current index and the total count.
And the length of the sequence.
Length of the sequence, right?
Yes.
I don't know if Brandon is still with us. Integer.
I'm still with you guys.
Nice. Index. And then length. Is this that we add to the accumulator. So this should give us our value, right? Let me try this and just ix. Oh no.
Could we? Okay.
Why do we have 50? Sorry? What did we miss?
It's because that's like let's see.
Because I think we should get 178.
Yes, for the first term. So it means
there's something we've missed here.
Yeah, you aren't getting the value from sequence. You're just multiplying it with the modulo. So this needs to you have to map
so
this to
this
the multiplier. So you have to
okay.
that whatever the value of that should be the value of the index of the value in the multiplier. So you can cover that in the yes.
Instead that multiply index. Let me just do that, and then value will be enum.add. So wire. Right, so now we have here, so I can now come to a peak and multiply them. Now let's see if you're going to get 178. Nice. Now we have 178. So we now need to keep doing this.
So the question is how?
We say we need to have some recursive function, right?
Yes.
So my thinking, so this recursive function is supposed to take in the current sum, or rather the current, yes, the current sum and our new sum. Now the current sum and the value that we have right now. Am I even making sense?
We need
So,
to get what is the base case? That's the question. If you're doing recursive, what's the base case?
what do
I
you
think
mean
it's like the point at which we know to terminate.
It's when we know the current sum, the sum, and the value.
The previous.
Yes.
Is equal to the previous
value.
The previous
Current sum, previous sum.
Yes. Otherwise, call that.
So let's call our function again. So if that isn't met,
we need to run our function with the new parameters.
so we're going to need this previous sum, right?
Yeah.
Huh?
Yes, you're correct. So
let's put that here. Paste it here. So we're going to get digits of the current sum, right?
Yes.
Sum will be equals to this. Give my show the right thing. And then after we get sum, we call our recursive function. So it will be sum, and then this one will be the previous sum, the current sum. Voila. This should work, right?
let me just go through what we've written.
Okay. So if we have our function that recursive, it's taking the current sum, the previous sum, we know that if both of these are equal, then that is when we return, right? So in this case, when we start over, let's say we start over, our current sum is 1, 2, 3, 4. 5, 6, 7, the one that we have. So what will happen is I will take the digits of this guy, what we did. This is the multiplier. And then I get the sum of the digits multiplied with the multiplier. That's the first round that we've done. With that, we'll have gotten our current sum now, which is here. And then we pass in the previous one that was passed here. And the process repeats. So if both of these are going to be equal, if we're going to reach, remember this first round, you're going to get 178 as the sum. And then the current sum now is going to be 1, 2, 3, 4, 5, 6, 7. Right? Is that okay?
That's okay. I was just looking at how we are put passing in the current sum.
Yeah, but this is exactly that's what we've talked about right now. So once we finish this first round, we're going to get 178, what we've done here, right? We're going to get 178 as the sum. And then current sum is still going to be 1, 2, 3, 4, 5, 6, 7. Now we're going to reach here. Is 178 the same as 1, 2, 3, 4, 5, 6, 7? No. So we're going to come here. We ignore the previous sum. We continue with 178 to get the digits. We do the same. Then we call again. So maybe we might need to, okay, let me put this here. We need to make it more clean. Clear still not optimal. It's the solution that we have. So let's test this out. The answer is 79. What are the test cases? The first
You're
one.
getting 179, it's not 79.
We need to get 8529. Oh, no, I haven't even done anything actually. Oh, goodness. I didn't do anything here. So we need to copy.
Yes.
So our current sum is
You're calling
10.
it. Yeah.
That is when you can give it 0, right? That okay? So let's test it out. Right.
It runs. Nice.
Yes, so there's one solution. Do we have another one?
This is like the most straightforward way, because I think they have already broken down for you the approach.
How about what if we use pattern matching?
So they are
Okay.
maybe that now this is like improving all the code.
Yes, just to improve it. Just
One
thinking
is
about something else.
You could let me see something about your code. So there's some things that maybe some performance things, like the fact that we're calculating the length of the multiplier on every single run, that could be improved.
Exactly. Okay. what I had in mind is, what if we have, so this recursive function, what if it could keep on receiving lists? What we have on this, okay, actually it will be receiving 3. Oh no, how many items will it be receiving? So we need to keep track of, I was thinking maybe we need to keep track of the current digits list, the one that has been reversed. The second one we need to keep track of is our multiplier list, this one. The third one that we need to keep track of is the current sum. So we need to keep track of the current sum, the previous sum. That'd be a lot of argument. And then, okay, the idea is for every iteration, what I do is I take the first element this side, I multiply with the first element on the other side. And then I call that function again and again. If this list is empty, I just start again. Okay, something like this. So let's say we have our n here. That's first. Just n. I have multiplier plus n current sum sum. Okay. So for every iteration, what I'm just doing is taking this, I multiply by this.
Oh, so you are using this this idea of you are breaking down the list as you go.
And then the next iteration, I'll be taking this.
Just rest,
this.
pass on rest. Okay.
Yes.
So how will
when
we? Yeah. Oh yeah. So I want to ask you how we will pass down the previous result to the next, because we are summing up the values of n times m.
We're summing up
the values of n times m.
Yes. So here they are the fourth, the third and fourth argument.
Okay.
Yes, they're all here. So when this multiplier list is empty, we just restart it again. If it's empty, I'll just call this start recursive, and then I start it again afresh with this list.
Values.
Yes, so this new values. So it will be something like so when this is empty, and
I think because we don't care about the oh yeah, okay. I get why you're doing the first bit.
for this guy, I'll just give them this. And then I'll just have the initial. The cycle continues.
That is throwing an error. Because initially is
Oh,
not
yeah.
defined.
Yeah, so we can define it as a module attribute here. I can have it here, or I can even have a function that gives me this.
Let's use the attributes. I think it's simpler.
Simple, right?
Yeah. You have a type
there.
Initial.
Ah, yes. Yes. So we have that. And then I'll have this. So for this scenario, what do? We take n, I multiply by m. And what do I do with that?
That does the, so that is doing the bit for the enum.reduce, but it's not doing the reducing just yet.
Yeah.
That's summing up this value.
Mhm.
Let's see how we can
So we still need the accumulator somewhere.
Yeah, so maybe we can rely on current sum to be sort of be our, okay, could we introduce another one, like an argument that keeps track of what is our current sum, and then we only do the check when we are at the end of the what's the word, the digits. So when n is empty, we could have another pattern check for when n is empty. That's at that point we know for sure that we're at the end, and we have like the sum for current, and then we set previous sum from there.
So we proceed until this list is empty.
Until it's like the first one is empty, not the second one.
Oh yeah,
and the other one is empty, yes. Then at that point we know.
Once done.
Because then we know, so we could basically be using like current sum. So we could do n times n plus current sum, and then call itself again with current sum as the basically the accumulated value from the previous operation. And then when we get to n is empty, that's when we check if current sum is actually equal to previous sum. If it's not, then previous sum is set to current sum, and the pattern continues with now n being the current sum.
Yeah, I get you. So we'll have this.
It can just call itself again with current sum and previous sum as was passed before. We will have a specific one to check, like the function that we check. The function that we check. Yes, that's like the one that you basically just bring everything to a stop. That's the point we care about actually.
Yeah. Continue. And now we have that. So this is going to be rest n. This is going to be rest m. Then we have this guy. When this is empty, right?
We don't care about
when
m at this point.
Yeah. Oh, yeah, we also don't care about any of these m's. And then we say when
And previous sum. Current sum. Then I think we need to do this similar function for like when now to pass to pass in the new value of previous sum.
Previous sum, right?
Yeah, because we need to update the value of previous sum at some point.
Yeah, so that is the case we have right now. So this is already empty. Day is not the same as days.
Yes.
Right? So
I think it's the same function as line 96, but just that the fact that this time you will recall it back, but with previous sum being equal to the value of current sum.
yes, yes. So now current sum is the previous sum, right?
And I wonder.
And now what is the current sum? Is it 0? Now we can set it at.
Yeah, you can actually resetting it is the correct thing, yes. So that it doesn't prematurely come to an end, because it will call the function where current sum is equals to previous sum.
Yes. And then we start again our initial multiplier.
Yes.
And then this guy will now be the digits and then the reversed one.
It will be the new value, it will be the value of current sum. Just go down. No, it will not be it will not be that one.
Why not?
It will be current sum because at this point, like,
is it not this one?
It is that one. But
right.
Yes, that one. Yes, correct. I forgot that you're passing in a list.
Yes. Oh no. What have I done?
Yes.
Oh, I clicked.
But you haven't called it yet.
Yes, actually I pressed Control S.
Oh, it runs on your save.
Yeah. Okay. So this should do it, right?
Yeah. Looks good.
Okay. Let's try it out. Start Cassie 2. And what we were starting with is actually this guy. So let's start the digits. And then initial. Then the current sum is 0. What is the previous sum?
We can use the previous sum as the digits that we were given as n.
N.
1, 2, 3, 4, 5, 6 thing.
Oh no, isn't that not the current sum actually?
Yeah. Because we will compute current sum, so previous sum can be that one. That's for instance that the number is already, like assume the number was already 87, for instance.
Mm-hmm. Oh yeah, got you. So first compilation error, undefined function cursum. Where's that? Oh, yeah.
Line 5.
Oh.
Yeah.
Brilliant.
So the recursive function is quite simple, but
yes,
a little bit difficult to follow.
Yes, it's difficult to follow. The only thing I do love about it is we didn't actually use any of the modular functions. Right. Okay.
Is happy.
Yeah, I think this was that was a bit simple. But yeah, I think that was a nice session. I think we also out of time. So now where's Zoom? I think I can stop sharing. Oh, no, I'm back. Oh, we had Amos and Brandon left. Hi, Amos.
Hi, Frank.
It's good to hear from you. So yeah, we've come to the end of the session. For the next one, so what we want to try to do is to introduce a project. We are still looking for one so that we can keep doing it just to refresh in our minds. Because remember, for these Codewars, we can't really practice like the OTP stuff. And I think that is like the most interesting bit in Elixir, I would say, aside from pattern matching. So we are looking for a project to do. I don't know if you guys have one in mind, something that you can do to keep us busy and also to keep us learning for the upcoming sessions. Yeah, so that is what we want to do, and then we'll let you guys know. But if you have any, feel free to send it in the WhatsApp group, or maybe you can also just contact me, you can DM me on WhatsApp. Right. Actually, it can be a game.